In this tutorial, we'll be exploring quantization-aware training, which is a concept that counters the potential drop in accuracy when we convert our TensorFlow model to a TF-Lite model and also apply some post-training quantization like we did in the previous tutorial. We'll be looking at an image classification problem, and we'll be using the MNIST dataset. So we'll be treating that as our baseline model. And then we'll be doing some comparisons between TensorFlow models and TF-Lite models, as well as TF-Lite models with and without quantization awareness, and so on. So the first thing we'll do is to install all the libraries that we need. And so we'll be looking at the MNIST dataset, and this is the same as before. We just load the MNIST data set. We split it into train and test. We normalize our train and test images. And we go ahead and define our baseline model. So the baseline model contains a convolution layer, a max pooling layer, and then finally an output dense layer, which has 10 neurons corresponding to the 10 classes of the MNIST data set. We define our optimizer and our loss function, and we go ahead and compile our model. So question 1, why do we not define a softmax activation function in our final layer of our model? So if you see here, usually we have a softmax activation function defined, but in this particular example, in our loss function, we set the flag from logits equal to true, which indicate that we actually calculate the loss with our logit values and not our probability distribution values, which is the output of our softmax activation function. Next, we train our model using model.fit on our train images and our train labels. And again, here, instead of using our test data as our validation data, we'll be splitting 10% of our training data and using that as our validation data. So we go ahead and train our model. We see that our accuracy is around 91% and our validation accuracy is around 97%. And we go ahead and look at our model.summary. So that is our baseline TensorFlow model. We're going to fine-tune this baseline TensorFlow model with some quantization-aware training. So what quantization-aware training does is basically mimic the inference pipeline and estimate the possible errors that could arise due to conversion to TF-Lite model and also post-training quantization. And with this knowledge, the model is able to learn parameters robust to these errors. And this is an attempt to essentially increase the accuracy of our quantized model. So we bring about this using the TensorFlow model optimization library. We define or instantiate the API, tfmod.quantization.keras.quantizeModel, and then we use this as a method on our TensorFlow baseline Keras model. So now this Q-aware model is our TensorFlow model with quantization awareness. So with this new defined model, we recompile with the same optimizer and loss function. And just to give you a summary of this new model, the layers remain the same, but there are two differences. Each layer is prefixed with the word quant, indicating that these layers have been quantized in the sense that they have some quantization awareness. And also, quantization awareness introduces some non-trainable parameters, such as maximum or min values of a particular range that could be used as knowledge to quantize your weights and intermediate outputs and so on. So these non-trainable parameters that have been injected into our model are the ones that bring about this awareness into our model. So these non-trainable parameters are included here and there. For example, max pooling usually does not have any learnable parameters, but it has one non-trainable parameter here. And yes, we go ahead and train this fine-tuned baseline model. So we just train it on a subset of images. So we know that our training data set has around 60,000, but we are training our model only on 1,000 images, sorry. And this is just to show how powerful quantization-aware training is, in the sense that even when it's trained only on 1,000 images, it's able to do pretty well and get an accuracy of 96%. Okay, so now that we have two models, we have our baseline model, baseline TensorFlow model, and our TensorFlow model with quantization awareness. We test both these models on our test dataset, or evaluate both on our test dataset. We use model.evaluate on test for our baseline model and save the accuracy. And we also run Q-aware model.evaluate on our test images and save the accuracy. And we see that the accuracy has not changed, or essentially it persists, even with the changes that we brought about using for quantization awareness. Question 2, what is the advantage of quantization-aware training? Like I said, it sort of mimics the inference loop, and the parameters that the model learns now is with the knowledge of possible errors. And in this sense, it's able to train or learn parameters that are robust to potential errors brought about during quantization. Okay, so now that we have our TensorFlow model, we're going to convert them to TF-like models. So we are going to in this section, we are going to be using the quantization-aware model. We are going to load it, and we are going to use converter.convert to convert this model into a quantized TF-like model. So just note that we're also introducing dynamic post-training quantization with this flag. And so once we do converter.convert, we get a model that has post-training quantization as well as quantization awareness pre-training. Okay, so that is this model. Question 3, how is tf.lite.tflite converter from Keras model API different from the from saved model API we used in previous tutorials? Can you think of a disadvantage of the former method? Okay, so if you notice here, we use from Keras model, and then we insert our model name or model variable. In the previous tutorials, we used to do from saved model, and we used to basically give or pass the path to that saved model as a parameter. So that is essentially the difference. From Keras model loads a model that's saved in the session. From saved model loads a model that is saved onto disk. And a disadvantage of the former would be if the session runs out or times out, then you would have to retrain your model again before loading it onto this TF-Lite converter. In this application, it doesn't make too much of a difference because, as we saw, our model, we are really training it only for one epoch. So it doesn't take too long. Hence, using from Keras model is fine. So next thing we'll be doing is actually running inference on this TF-Lite model. So we define our interpreter, we set tensor, we then run inference, we get a prediction out of the output by using argmax. And then finally, we test or compare our predictions with the actual test labels and calculate the accuracy. So this evaluate model or this inference model function takes in your interpreter and it returns an accuracy. So that's what we'll be doing here. We define an interpreter. So instantiate the interpreter, link it with our TF Lite model. Again, just to reiterate, this model is the model which has post-training quantization as well as quantization awareness. We allocate tensors to the interpreter, and then we evaluate our model or call this user-defined function on our interpreter and save the corresponding accuracy in this variable. So we have two accuracies now, Q-aware model accuracy, which is our TensorFlow model with quantization awareness, and then TF-Lite quant QA accuracy, which is our TF-Lite model with quantization awareness as well as post-training quantization. And we see again that the accuracy persists. So with quantization awareness, and when we convert to TF Lite and do some post training, the accuracy is still around the same. So question 4, why do we allocate tensors to our interpreter? So this is a step that TensorFlow does because it pre-allocates tensors linked to all parameters and weights and activations corresponding to our model. So it's just an optimization trick to pre-allocate tensors, and that's why we have to call this method called allocate tensors. Okay. Now in section 3, we'll be looking at 3 different models or 3 different combinations of models, and we'll be comparing them in size as well as accuracy. So our first model is a baseline TF Lite model. So what this model is our TF or our TensorFlow model converted to a TF Lite model, but this has no post-training quantization and no quantization awareness. Okay. Then we have our second quantized TF Lite model, which is a TensorFlow model converted to a TF Lite model with dynamic range quantization, but no quantization awareness training. And then our third one is a quantized TF Lite model with quantization awareness. So which means it's you take your TensorFlow model, apply quantization awareness training, and convert that to a TF Lite model, and then apply post-training quantization as well. So the third one essentially has post-training quantization as well as quantization awareness training. And this is actually exactly the same model that we used in section 2. Okay. So our baseline model, use converter.convert on model. Okay. So model is our baseline model. This is different from the Q-aware model that we use in section 2. Use converter.convert and then use interpreter to run inference on this model and then save the corresponding accuracy. For our second model, we load the baseline model again with no quantization awareness training. We then set this flag to indicate that it has dynamic range post-training quantization. Use converter.convert and then use our interpreter to run inference on this model 2 and save the corresponding accuracy. And our third model is exactly the same as what we did in section 2. And the corresponding accuracy is TF Lite quant QA accuracy. So if you look at the variables, it's TF Lite baseline accuracy, it's TF Lite quant accuracy, indicating this post-training quantization, and there's TF Lite quant QA accuracy, which indicates post-training quantization as well as quantization awareness training. And we look at the accuracies and we see that they're all very similar and there's really no drop in accuracy. But the most important thing to observe or the trend that should be observed is that our model 3 which has quantization awareness training, has a higher accuracy than the TF-Lite model with no quantization awareness. So these two are comparable because one has quantization awareness training and it has a slightly better accuracy, and the other one does not have. And this is important because the whole purpose of quantization awareness training is to improve the accuracy. Next, we compare the three models with respect to size. So we use the os.path.getSize function to get the corresponding sizes of our three models. So when we print them, we see that our baseline model is around 0.08 MB. Our quantized model and our quantized model with QA are both around 4x smaller, with Model 3 actually slightly bigger than Model 2. But this is what's expected because while post-training quantization focuses on compressing the model and reducing the size of model, quantization awareness training focuses on improving accuracy. So while this model is actually slightly smaller than this, the Model 3 is actually better or has higher accuracy than Model 2. And finally, we just observe these differences in terms of bar graphs. So this is the bar graph for model performance or accuracies between the baseline model, the quantized model, and the quantized model with quantization awareness training. Observe the scale. So the difference is very minimal. It just seems greater because of how precise the scale is on the y-axis. And this is the difference in bar graph for the sizes of the three models: baseline model, and quantized model with QA, with the baseline model being the largest.